Everybody, I'm Jeremy. I'm going to talk to you a little bit about big data in JRuby today, and this is more of an overview talk. We'll get into a couple of smaller details on Hadoop stuff when we get down in there. But initially, this is just sort of an overview of what big data actually is, and then some tools and some procedures and stuff that you can go through to help you if you have a big data problem. So the first question I have is, what is big data? Who's got a definition? Come on. Raffle scale. Okay, that is a great definition. Nick, of course, has one. More than I can put on my time machine backup. Okay, that's a good definition of big data. There's lots of definitions for big data. Where there actually are some official definitions. All right, everybody read this. It's kind of dry. Big data applied to large data sets whose size is beyond the ability of commonly used software tools to capture, manage, and process data without a reasonable elapsed time. Okay. So what Nick said. Yeah. It doesn't fit on a time machine backup. There's also another one that Gartner has. Of course, they get involved in all sorts of stuff like this because it's big business and enterprisey and all that kind of good stuff. So increasing volume, velocity, and variety of data. I personally. These are, they're dry. Anybody can think of them. This is my definition. One of them. Or who's had this happen? Yeah. Nagios, low disk space. There you go. All that kind of good stuff. Or the ever popular, that data processing job, the one that takes all day to run. It's got to crunch all that data. Yeah, we need to do it over. It's wrong. And we need to run it every day on yesterday's data by 8 a.m. So who has that problem? Okay, yes. And it takes longer than 24 hours to run. Exactly. So I asked you guys, and I also did the Chad Fowler approach and many other people's approaches. What is your definition of big data? And they kind of broke down into 3 different areas that I can kind of define. One of them is that's a lot of data. So I personally like CJ's, which is if Active Record can't do it, it's big data. I think that's a good one. JEG too. Everyone knows James Edward Gray, awesome guy. He says it's big data when I have to use a specialized database. So that's also a decent one. In terms of big data, different people have different volumes that they think are quite a lot. Does anyone recognize this image? Yeah. Tim, you know it. This was actually generated with Ruby. So how many of you know Ara Howard or heard of Ara Howard? Okay, yes. All those of us in Boulder are big fans of Ara. So years ago when Ara was working at the Earth Observation Group, this basically is the night lights from the lights of Earth from space at night. So these are highly populated areas and all that wonderful, great stuff. So they have all this satellite data, raw satellite data, and some of it cleaned a little bit, and I don't know all the processes they go through. But someone decided they wanted to buy a lot of it. And by a lot, I mean all of it, which was 10 petabytes. So who has 10 petabytes of information? Oh, all right. We have one. In terms of 10 petabytes of information data, I actually was looking at the Backblaze. They had this great blog post a little while ago about adding more space and doubling the size of their servers and all this kind of great stuff. 10 petabytes, I think, is 2/3 of the total amount of data storage that Backblaze currently has in their data center. So everyone who backups with Backblaze across the entire world, 2/3 of it was bought by one company from a volume perspective. So to get that data to the customer, they had 5 tape robots putting the data on tape for 30 days. Shipped it, UPS or FedEx or, courier. Huh? Station wagon, yes. I'm about to use that quote. You know which one I'm talking about. And it was $75,000 worth of tape to start with, just to write it once, and then the customer spent 30 days reading it off of tape. So who knows the Andrew Tannenbaum quote I'm about to use? Okay, all right, there's 2 of you. Never underestimate the bandwidth of a station wagon going down the highway with a box of tapes in the back. Okay, the latency sucks. 60-day latency is not good, but the bandwidth is tremendous. So if you feel like it, somebody calculate how long it would take to do 10 petabytes of information over your 50 megabit link at home. Somebody run the numbers. I haven't done it yet. So that's a large volume of data. It wasn't headed there fast, but that's another thing. Another definition that people kind of came up with when they were talking about, when I asked the question of what is big data, they said a lot of data, a good chunk of data heads my way really, really fast. Charlie Baker, is he in the room? Yes, Charlie, okay. He said 9 terabytes of compressed data coming at me every day. Not too bad. More than processing that fits in RAM, or, yeah, lots of data headed your way fast. For an example, how many of you use Twitter? Okay. Do you realize that your tweet is more than just 140 characters? You know, the actual volume of data that's in a tweet as a consumer of someone who does tweets is about 2,500 bytes, which includes like the tags, the location if you have it turned on, a lot of your author profile, all sorts of lovely information. So this is a while ago, 155 million tweets a day, which is 16 gigabytes an hour, or 4 megabytes a second, or 33.8 megabits. Who's a networking person in here? Knows volumes, which is the majority of an OC1 line. So that's a data coming at you very, very fast. So how many people have an OC1 line at least into their data center, or wherever they're getting data? There we go, 2. Yeah, not bad. So this is all from GNIP, which is a company that actually processes Twitter data, and you can repurchase it from them and all sorts of good stuff, or subscribe to it. The other piece that people were talking about, we've got large amounts of data coming at you very fast, and then what do you need to do with it? Actually, I like Nutty Combs' example here. He says it's big data when order login is too slow to process it, which is kind of, you know, when you say, hey, when a really fast algorithm can't do it, then, you know, it's big data. And one that I have to deal with on occasion to add to this is how long do I need to keep this amount of data around? So I've got a lot of data coming at me very fast. I have to do a lot of work with it, and I have to keep it around for a while, maybe process it again later. So my personal term for big data is any data that makes me feel uncomfortable. Or, as also you can say, how fast and how often can you boil the ocean? But never fear, help is on the way. Anyone know basics instructions? Yes, okay, very popular comic, I like it a lot. The first help I'm going to try to give you is you don't need big data. So a lot of people think you need big data, but you need to understand why you think you need big data. Daxus, who is probably not quite here yet, has a great blog post. He's in the state. Okay, good. He's in the state. He has a great blog post on the problem with big data as a rant. So there's a good chance that when you think you have a lot of data, you actually don't need it. So based on your situation, it's probably okay to throw a lot of it away. For example, say we have 155 million things. I'm not going to say what these things are, but say you have 155 million of them. How many of those things do you need to make an analysis of the population as a whole? With these criteria. 1% error tolerance and 99% confidence. Anyone want to take a wild guess? 10,000? All right. Well, you guys are actually pretty close. I was thinking people were going to guess a lot more. You actually only need 16,588 of them to make a really good analysis of the entire population as a whole. So if you had 155 million things that were 2,500 bytes apiece, it's something like 34 megs of data, which is really easy to process in a reasonable amount of time. So the one thing I'm going to say is about this is if you need to understand your problem domain. There's a very good chance that if you think you have a big data problem, you don't. You actually just need to sample it and process the sample. So now, there are cases. So initially, you don't need big data to start with. Assume that. But after you've decided that, or you've made the decision that that assumption doesn't work, and you do need to process a large volume of data in a timely manner, maybe continually, and store it for a long time, there are some other tools out there to help you out. And this is where we're going to talk a bit about the big happy Hadoop family. So how many people have used any portion of the Hadoop systems at all? That's not too bad. So anyone, feel free to tell me when I get something wrong. It's quite possible I will. We're going to start with the base piece of the Hadoop ecosystem. And that's where we're going to store a lot of data. And also in a very fault-tolerant and linearly scalable manner, according to the docs at least. So this is HDFS, or the Hadoop Distributed File System. So we're going to take, for example, a file. That file is across the top. Anyone remember the computer science way of showing a file as blocks, all that good stuff? So we're going to talk about this file that's 9 things wide, 9 blocks. In Hadoop, when we talk about block level stuff, everyone on your Mac and your Linux machines, a block of a file is generally about 4K. In Hadoop, or in HDFS, a block is probably 64 or 128 megs. So you need to have larger files generally in here. So this file is, maybe a gig, a couple hundred megs, something like that. So the way HDFS works to store a file in a distributed and fault-tolerant manner is it basically takes each block and then it spreads it, duplicates it, and spreads it across different nodes. So you've got this file, which is basically a whole bunch of different blocks, and it's going to split the blocks up and put them on different nodes. So each one of these different data nodes is an actual physical machine. So you've got your 9-block file. Every block is stored 3 times across a whole bunch of different systems. So you can have some of the machines go down, and you'll still have the full amount of your data. So the question is, how does HDFS and JRuby fit together? Not really. So, hey, HDFS, it's a very core system. How many people actually write Java to write directly to HDFS? Probably not as many as you think. So you could use, say, something like Fuse, or if you wanted to, you could use the straight jar, talk to it in JRuby, write a file into HDFS, and be done with it on that front. So mostly I wanted to talk about HDFS just to give you a baseline of saying, okay, this is a fundamental infrastructure for the Hadoop ecosystem. So next we're going to talk about how to process lots of data. So how many of you know of MapReduce? Come on, raise your hands. All right. How many of you use Hadoop MapReduce? How many of you use something else? What do you guys use? Riox MapReduce. Any others? Yes. Mongo MapReduce. Okay. All right. There's a couple other. I can't remember their names, but there's a couple other actually based on Hadoop and other types of things that are MapReduce infrastructures. I think there was an old Ruby one that was called Skynet, which I don't know if anyone used. But the basic fundamental premise of MapReduce is you have embarrassingly parallel problems. So these are problems where you can take the input, you can split it into completely autonomous chunks, take those chunks, run a process on them, map process. You take your map, and you have basically tuples. For each one of the map inputs, you're going to do a process on it, and you're going to get out your output. And then the reduce input is basically all those map results grouped up. Everyone that has a common key, all the values for that common key will be put together in a big group, and then you'll run the reduce on it that takes all those individual keys and those lists of values for that map and produces something else. So it's embarrassingly parallel, as opposed to something like weather simulation or things where every stage of the system has to interact with a whole bunch of other different things. So MapReduce is embarrassingly parallel. So remember that when you talk to your science guys. So, and the way this does it is you have and the way this works in Hadoop is you have your job tracker and you have a bunch of task trackers which are sitting there generally in parallel with your data nodes. We've got our little file down here with all those different pieces. You submit a job, which includes the MapReduce stuff and some other meta information about the job. And then the job tracker says, hey, we're going to take this and we're going to split it up across all the different data nodes. Each different data node and task node will process a piece of the file that's local to it. So this is where Hadoop comes in. It says, oh, we've got this really big file. It's spread across all these different nodes. It can take your actual map and reduce process, take the map process, and give it to each one of these, call it file block, and run it locally so that you're actually moving code to the data versus moving data to the code, which is what we typically do in a lot of different things. So this is moving code to the data. Now, how does JRuby fit into this? Well, it's complicated. There's lots of ins and outs, lots of what have yous. This can make you feel what it looks like. To understand a little bit why this is a bit of a problem, we have to look at how, in a general sense, how job submission and job running works. So in the generic sense, when you're submitting a job to Hadoop for MapReduce purposes, you build a job jar file, you submit the jar file to the tracker, the job tracker gives the jar to each one of the task trackers, and then each one of those task trackers will do the appropriate map and reduce test by essentially looking up the class and feeding the data through it. And basically, there's 2 points where you actually have access to the entire system. One of them is up here, when you're packaging up your data, and the other one here, which is basically at runtime. So these are the 2 areas where when you're using JRuby in relation to Hadoop, you have the potential for actually doing something with the MapReduce system. Now, there are a couple of things that are already out there. One of them is Hadoop. If you Google Hadoop right now, you won't get this project. There's something a little more recent, which is taking the name Hadoop, and it actually has nothing to do with Ruby. So, and in Hadoop, because you're doing, you basically you have the Hadoop command line instead of the Hadoop command line. So that's actually subverting the bootstrapping process of submitting the job, and then you have the way that you actually implement your map and reduce tasks is in Ruby by inheriting from Ruby classes, which are actually essentially Java extensions. So you have these the Java code that's in the gem, and then you inherit from those classes, and it sort of bootstraps it that way. Unfortunately, it's a little old. It hasn't been updated in a while. So that's one aspect. In fact, this probably doesn't even have support from some of the more recent MapReduce APIs. So then we talk about JRuby on Hadoop. This is another, basically follows the exact same approach. You have JOH instead of the Hadoop command line. Instead of inheriting classes, you actually just define methods in, say it was a top-level standalone script, you define setup, define map, define reduce, that kind of thing. And then those get packaged up together. And then at runtime, because this, again, uses Java shims, essentially a Java extension in the gem, and part of the packaging makes sure that JRuby and the JRuby on Hadoop stuff is all shipped and pushed off at the same time, you, again, have the exact same thing of a Java extension. The problem with this is it's been a while since it's been updated, and if you look through the code, it actually only supports a small subset of possibly your inputs and outputs. So then there's another one, which is Hadoop Papyrus. It uses Papyrus. We've got, see a pattern here. We've got packaging and runtime. It's basically your interfaces into where JRuby could fit in. So we've got Papyrus, and Papyrus is actually built on top of JRuby on Hadoop. So it implements a sort of a DSL style for doing MapReduce programs. And again, it also hasn't been updated since 2010. So the problem is none of these are actually very useful for us as a programmer. They're not great. It actually, sitting through and looking through all the source code is the only way I figured out how they actually work and actually how to use them. So there's a couple other approaches where JRuby can fit in. Is anyone using cascading? No one? All right. Oh, one person using cascading. I haven't actually used it, but this looks like a pretty decent possibility. It's more of a higher level language, but it's got full JRuby support. The folks at Etsy have provided JRuby support for cascading. It's a way of plugging workflows together as a whole data processing API. I've only known about cascading for a few weeks, so this is just a reference for everyone else. And the other way to do Hadoop MapReduce processing is with streaming. And this is the way Hadoop provides a facility for you to say, hey, my map and reduce processes are actually just going to take data on standard in and emit it on standard out. So that's if you could actually write your MapReduce programs in a shell or any other program that doesn't actually have to be Java. Who's using the folks that are using Hadoop? How many of you use streaming? One. Okay, one uses streaming. There is a performance hit on this, from what I understand. And Mr. Flip, who's part of InfoChimps, he has a project called Wukong, which helps encapsulate all the streaming, inputs and outputs and putting all these other stuff together. So these are some other approaches, and then we have these 3 other gems, which are starting to do a little bit on the front, but actually I want something a little bit different. I would like to use the normal Hadoop command line. It's there, might as well. It just needs a jar, and you could submit it, and everything works. And I'd like to actually inherit from the Java classes that exist, the standard way you would do MapReduce. We have JRuby. You could inherit from mapper, write your map function, inherit from reducer, write your reduce function, and everything would be great. Unfortunately, it's not written. I'm going to take a hand at it if I can. Gonna have to work. It looks like there may be something we have to work with in JRuby itself to make this happen. So I'm going to try to help out, the team and see what's going to happen, and we'll go from there. But there's actually just a little tiny piece of linking JRuby and Java together, with in particular case for Hadoop, and we may be able to just have full-on, straight-up JRuby, write your MapReduce jobs in Ruby and be done with it, which is really cool. Who would like to see that? Yeah? All right. So keep your eyes out. See what happens. So that's a little bit of the MapReduce. So that's how JRuby can fit into the whole MapReduce ecosystem. So we've got MapReduce. We've got the HDFS. What are those actual files we're going to store in HDFS? So what do you guys use? The ones that are doing it. What are your files that you have on your HDFS systems? File formats, anyone? No? Okay. So we have a lot of data to store. How many have heard of AVRO? It's actually I actually like this as a container file format. AVRO itself, it's not a Hadoop project, but it's an Apache project. You have a very rich data structure document. It is sort of a JSON based, and it's a binary format that's very compact. It also has protocol buffer, thrift-like, network ability. But the thing that I really like about it is it actually has a container file structure. So you're able to write your records into an AVRO file in a very compact format. There's no code generation involved because the schema that's defined at the header of the file, any client, any library that needs to open the file can just read the schema and they'll know the entire structure of the data. So it's basically record level data with the schema at the head of the file. It's MapReduce friendly. In terms of it's got sub-blocks within the file, and I'll get into that in a minute. And it actually supports compression. So this you can use outside of Hadoop, period. I mean, it's a standalone library for a container file structure for storing data. If you ever have anything that's CSV, you should probably think about using AVRO instead. Another thing is it's language neutral. So the AVRO project itself has implementations in Java, C, C++, C#, Python, Ruby, Perl. I think there might even be a Lua one, but they're all completely language-independent ways of doing this entire, the AVRO library and the container file structure. So if you think about the container file structure, again, we've got our big 9-block file. The way AVRO works is we'll just take a look at these first 2 blocks. Say they're stored on 2 different data nodes. And this is actually how AVRO takes advantage of being, in addition to being a good container file structure on its own, it can also provide significant advantages when you're using it in HDFS. So if you think of these data nodes, if you think of 1 and 2 as part of the first beginning of the AVRO file, and these dark and light stripes are sub-blocks within the file. So say we have that task that goes out, it's hitting node 1, it needs to open up the file, and it needs to be able to go through and work on the data that's just local. But it needs to do it at a record delimiter. It doesn't. In this case, for AVRO files, it's not going to do it at a record delimiter, it's going to do it at a sub-block level delimiter. So it's going to process along, and it's going to process up to the end of the first file block that's not on the local block. So the amount of data that has to move between data nodes in Hadoop is reduced to just about, probably less than just a few K. And then task 2 can pick up there from that point and go further on. So this is the way that AVRO works out well in the HDFS system and works well with the task trackers and stuff. If you're using something like a tarball or a straight CSV file, CSV file might not work too bad, but especially if you've got a tarball, then there's problems with that in terms of splitting the file into different chunks. And a lot of people that are doing tarballs in Hadoop, they'll actually make sure that their tarball files are already pre-split. So every file is already just 1 block long, which kind of defeats the entire purpose. So in terms of just AVRO as a whole, say I had 5,500 records. All of these maybe around 2,500 bytes or something like that. If you just look at the straight JSON, it's 12 megs. And it's a 2 meg tarball. If you convert it to an AVRO file, it's actually just 3.6 megs, and that's with no compression period. when you think about it, these are JSON records, so all those keys that are in every single one are duplicated. So every single one, there's a lot of overhead in just the keys in a JSON file. The same way there's a lot of overhead in XML when you've just got the tags. So you might look at like 80% of an XML file might just be the tags. Well, in this case, it looks like about 60 to 70% of the raw data is actually the JSON structure. It's supposed to be a compact format to begin with, but you still have these keys that are in every single instance. So just by converting to an AVRO file, which puts the schema at the top of the file, and then every record is just binary, then you've reduced 70% of the data volume just by stripping out essentially the keys from your key value pairs. And then those individual subblocks in the AVRO file are individually compressed. So you can use snappy compression, which is a really nice compression because it, like LZO, are these new styles of compression where it takes less time to read the file off of disk and compressed and decompress it. That time right there is actually shorter than if it was uncompressed and on disk. So there's a couple different algorithms, libsnappy, LZO. They don't have the best compression ratios, maybe only 50-something%, but you can read them off of disk and decompress them faster than you could read off of disk the uncompressed data. And it's pretty cool that way. So AVRO and JRuby, yes, we have happiness. With JRuby specifically, you could use the jar. I mean, it's just a jar. That's it. It's just a library. You could also use the Ruby implementation itself. So depending on the features that you need that I didn't talk about, you may want to use the Java or the Ruby if you just want some basic vanilla stuff. So this is a really good spot for JRuby, and I would actually, even just MRI or any Ruby you want, I would take a look at AVRO. If you are storing stuff in files on disk and you're accessing them via Ruby, I would take a look at AVRO in any case. One other quick one we're going to talk about is when you're dealing with lots of data distributed across a whole bunch of machines, you will need to be able to coordinate that. There's a tool called Zookeeper, which is essentially a set of servers that provide coordination services like group membership. So a bunch of people show up and say, hey, I'm available, I can do work, that kind of stuff. Distributed locks. You've got a process on one machine that needs to wait for another machine's processing to get done. And so it can do some sort of locking. Sequences, so sort of if you, to make things run in sequence, sort of a queue, or if you want to generate numbers or something like that, so that everyone has the same number, so it has increasing numbers. Watches, you want to say, hey, this is sort of like in the distributed locks, where I'm going to wait and watch for something to happen, and when it happens, I'm going to get notified. Well, that notification could be between machines. In the short and sweet, Zookeeper is a highly available file system. It's basically a hierarchical structure of nodes, call them Z nodes, and each node can contain other nodes or key value pairs. And that's pretty much the primitives that it has. So there's interesting stuff. When say I'm P3, I'm going to register, I'm going to connect to the Zookeeper server cluster, go to basically CD into app1 and register myself and put a P3. So anyone else who needs app1 services, they can go to Zookeeper. They could essentially CD into that node and then say, oh, list all of the available services for here. And so somebody who's unavailable, he could just disappear, or another one comes online, it can put a node there and appear. So there's a different way for doing distributed coordination. So Zookeeper and JRuby, Outlook is good. Zookeeper is a wire protocol. That's how you're going to communicate with it. And Twitter has probably the best implementation I've seen of the Zookeeper wire protocol. So take a look at it. If you need distributed coordination, Zookeeper itself is just a jar. It stands by itself. You'll need at least 3 servers running for your quorum to make sure everything looks good. But if you need to do distributed coordination, it's probably a good thing to look at. So say you have all this data, and we've been talking about it at the block level. What if you need essentially record level access? So you need low latency access to record level data. And in this case, the Hadoop project, or the Apache project that works on here, is Bigtable. So how many people use Bigtable or something like it? There's HBase. Cassandra is somewhat like this. And that might be the only implementations that are sort of around. But HBase is essentially, you can think of it as a really big grid with billions of rows and millions of columns. And every cell is optional, essentially. So HBase itself builds upon everything that we've already seen here. It uses HDFS-friendly files, so they're all striped and appropriately so that different chunks of them can exist on different servers, and the task managers can all talk to the appropriate data pieces. And it uses Zookeeper to coordinate everything. So HBase and JRuby, this is actually where JRuby shines in terms of the Hadoop ecosystem. It's at the top because HBase basically uses everything else under the sun. You can do MapReduce processing in HBase. Basically, you can access it via a protocol. And actually, one of the really interesting things is HBase ships with JRuby. So the HBase shell, or if you think of it as your Postgres or your MySQL shell, if you're going to say create table, all that kind of good stuff, select, do all these different things. For HBase, that is actually a customized version of IRB, which is pretty nice. HBase itself, if you wanted to communicate with it from a network perspective, it supports Thrift and protocol and also AVRO RPC. And there's then a couple of different interfaces. It also has the pure Java piece, and there's a couple of implementations. I actually implemented a JRuby called a JRuby extension to talk to HBase called Ashby. It seems to work out mostly well. And actually, that's essentially the gist of it. I'll start with some questions. Comments? Anything? No? Too much data? All right. So this is where we all need to go talk about this and drink quite a bit. So, yes?
Hey, get rid of data. Do you guys just sorry, I'm just for questions so it doesn't seem boring.
Oh, okay. So Dr. Nick is trolling for questions.
It's an interesting question. How do you know how long it is? Is it just pure business question?
Yeah, if you want to call it, it's data logistics. I feel like I've got data coming in, I want to remove data, I want to keep it for so long. A lot of that has to do with how you store it. If you're going to say, as data's coming in, I'm going to spool it here, I'm going to keep it here for an archive, this is a location, it's live data, and then for basically the data logistics, you've got to have a process that says, hey, this is the time and place where data is going to get removed. So the data meets a certain criteria. Most of the time it's aging off because of time. Maybe, or maybe, say you're storing some sort of financial or medical or something like that, you may have a specific time frame, maybe it's 7 years or 11 years or tax data or something like that. There's criteria that says this data can be gotten rid of at a certain point in time. So you'll basically have to decide. Most of the time it's a business decision.
I think you can add these rules, check the rules.
Yeah, you're going to have to write code to do that, to implement those rules. Yeah.
I take it these different systems take those rules or you have to run them?
You'll probably, say you've got terabytes, petabytes of data stored in Hadoop, you're probably going to have either a file system structure that things are organized by date, and you can just start removing stuff, or looking at the timestamps of files, or maybe the data in the files.
It's not like Memcache where you can
So not at all. Yeah.
So I don't think we're quite dealing with the amount of data you were talking about. We've got a whole bunch of things that we've been doing some calculations on, and we've been resisting the requests of one of our project managers to try and speed things up by saving some of the frequently done calculations as like a cached version of the data somewhere.
Sure.
Because what's a good guideline for figuring out when you might want to consider an option like that? Or do you ever want to do that?
So the question is, when should you consider essentially caching complicated values for a period of time?
Calculate computed values.
Yeah, computed values. My rough one is when it doesn't satisfy the business needs. If you're saying, okay, I have this data processing that has to take place every day, processes 24 hours worth of data, or maybe call it a week worth of data, and it has to be done every hour. Well, all the data that came in for the week minus the last hour, you might as well just cache that, and then have a rolling window of the data that ages off that doesn't apply to the calculation, and you can get rid of it. So yeah, if it can calculate once, and that output value is going to be used many, many, many times, why not cache it? That saves you CPU and costs you, bytes of data. Yes.
Yeah, for those of us who are just starting to be interested in learning more about big data, do you have any resources you'd recommend for blogs or podcasts?
Sure. So for folks just getting interested into big data and probably Hadoop in particular, if you can, there's been a couple of conferences this year called Strata from O'Reilly. I don't know if a lot of their just sort of like an overview of technologies and peoples and businesses that are involved in it. Those may or may not be available online. Some of them probably are. If you want to talk with Hadoop in particular, Cloudera probably has some podcasts and presentations, and they actually have a project, I think it's called Whir, which is essentially a bootstrap of getting a Hadoop cluster running in EC2 with a very minimal number of steps. So the one thing is getting a production system like this put into place can take a while to understand where everything goes, how it all fits together. There's a lot of moving parts. If it was simpler, that'd be great, but it's a complex problem and not necessarily going to have a simple solution. So yeah. Does that answer your question?
Yeah,
Okay, cool.
Yeah, actually, I am friends with folks at Dell who are building a packaged Hadoop solution.
Okay.
You can call up Dell
You
and
can call
order a Hadoop system.
So you can call up Dell and order a Hadoop system, yeah. There are other people that have, package deals that you can bring stuff up and put them together and order it online. Yeah. Maybe.
Well, a comment and then, so have you had any experience with Elastic MapReduce?
Have I had experience with Elastic MapReduce? No. But I know it exists.
Yeah. Amazon has a product where you can say, spin up a cluster. And it works pretty well.
Yeah. And actually, along those lines, somebody just put together, I think it was a 30,000 node Amazon EC2 cluster for an unnamed pharma company to do a calculation. And it was basically a supercomputer that cost like $7,000 an hour or something like that. It's very cheap for the amount of calculation it did. But continue, one more thing.
Well, what I was wondering is, like, I don't have any experience with Zookeeper, but I was wondering how hard that is to set up to do non-Hadoop things. Like, if you just want to distribute the job.
If you just want to use Zookeeper standalone, it's actually pretty simple because it is just a jar. You can just download the Zookeeper jar. It comes with some shells. It's a Etsy Zookeeper zoo.cfg. You set up the configuration. The how-to online for Zookeeper is pretty good. And you need at least 3, otherwise, because it's basically, I think it's a Paxos quorum, so you have to have at least 3 so they can vote and come up with the right solution. The one thing about Zookeeper, and Zookeeper doesn't, at least the last time I checked on it, it doesn't actually work well in EC2 because Zookeeper has extremely tight requirements on I/O latency for writing to disk because it's always persistent and it always makes sure that everything you do in Zookeeper is consistent across the entire quorum. So sometimes if your EC2 volume or your EBS volumes and stuff like that, they don't provide the minimum I/O requirements, so Zookeeper can fail in EC2. But that may have changed since the last time I checked. So yeah, yes.
What's the overhead on running Hadoop jobs with JRuby?
The overhead of running Hadoop jobs with JRuby, I don't know, because I haven't been able to get it working quite yet. So, but from an actual MapReduce, from internally using Hadoop or something like that, can't answer. Hopefully, I can answer that question before the end of the year. That'd be nice. Yeah, in the back.
There are 2 types of analysis you can do on the data. One is the real time, and one is like let's say you are getting stock market things, and then you want to calculate some stock market indices, some of those stock market parameters that you have to do that real time, and then you do offline processing. Like you collect the data of all intraday data, and you do calculate some of those stock market related indices. So the question is like HBase and the Hadoop, is it more suitable for real time processing, or is it like offline, like you gather data and
Yeah. So the question is this type of processing mostly used for, say, offline batch processing or online real-time stuff? Depends on your definition of real-time. Yeah, for in general, I would say Hadoop, in terms of MapReduce jobs, are probably not for real-time analysis. They're going to be more for offline because just the overhead of spinning up a job and submitting it, that you're talking seconds in that range. And then, of course, the data you're saying streaming to disk, you need to collect at least enough to fill up a block, otherwise it's not efficient. HBase, you could probably do more because all the stuff that it's committing, you have lower latency access to that data, but you also need to know that data is there. If you want to do more stream processing of data, actually Storm, which just came out, is probably worth looking at. There's another one that I can't remember. Off the top of my head. But if you need to do, if you have a higher, Flume. Flume is another one that might be useful, which is done by Cloudera. And those are probably going to be more in terms of if you're going to do stream processing versus more call it offline backup, where we're offline to maybe minutes, hours, depending on your data collection rates and stuff like that. More questions? No? All right, go to the AMP block party. We'll chat more there.